being here this evening. So, like, this talk will be given by my name is Swati Gavas. It is from this PhD in that. And she'll be talking about the aspects of gravitational clustering and structure formation in the universe. I welcome her and please give her applause for her.
Gravitational force is attractive only force. There is no otherwise evidence of repulsive gravity. So, because gravity is attractive only force, we see a variety of structures in the universe because of this. For example, the gravity tries to pull the matter together, and if the inward force is balanced by, let's say, atomic or molecular structure, those kind of force, we get a planets. Similarly, in stars, it is balanced by nuclear fusion. Or similarly, we see other structures. There are neutron stars, there are white dwarfs, where the force of gravity is balanced by some different kind of forces. Because of this, we see the variety of structures. So in this plot, what I am showing is this is a length scale. And the number on the y-axis, it is 10 raised to that exponent. So, for example, for planets, typically the size of the object is 10 raised to 6 meters. So, for typical planets, it is 10 raised to 8. And as we increase the length scale, we see different structures. So, for solar systems, typically we have 10 raised to 13 meters diameter, or let's say something like that. Then in the next hierarchy we have galaxies, where they span around 10 to 21 meters. Then we also see a cluster of galaxies. Few galaxies, a few hundred or thousands of galaxies present in a clump. We call them as a galaxy clusters, and size of that around 10 to 24 meters. So, what is beyond this? So, what stops us from looking beyond 24? Nothing stops us. Past few decades, there has been heavy efforts to map such a structure as Hubble space. So, I will be using the units megaparsec. So, this will be around 100 megaparsec. 10 raised to power 22 meters. Roughly is 1 megaparsec. So, the structure of universe around on scales of 100 megaparsec, we call it as a large scale structure. And what is it? When community, astronomy, cosmology community try to map such a structure in the observation through observation, we find there are many such surveys who did this task, and this is one of those surveys called SDSS. So, one digital sky survey, and this is image from SDSS. So, we are here at the center. This is our location, observing location. There is a Milky Way, and in two patches around our location, people try to map the distribution of galaxies around us. So, this is one side of the sky, this is the other side, and this is how they are distributed. So, this is called large scale structure, and so the unit, this is the radius of this circle would be around 500 megaparsec. So this is the really structure on those huge scales. So as we move, as we go in the further and further distance, we are seeing light from fast, more and more fast. That's why the structure will be according to that time. We are not seeing the structure at present time. The distribution will be affected. So this kind of field, the structure formation field, where your cosmology as well as the astrophysics matter. This is kind of boundary between cosmology and astrophysics. Now this is from the observation. We observe this with our telescopes, and this is the outcome of past 2-3 decades. Now similar times we also, meaning community, tried to develop a theoretical understanding of this structure, where this such a structure is coming from. This is not like some homogeneous distribution of it. You can see some patterns in it. So where this structure is coming from. And yes.
Ma'am, why those are the black parts in this structure?
This one, and this one.
Yes.
This is our own Milky Way plane. So we have lots of light from our own plane. So light pollution in this patches is so much that we cannot, detect this thing. Okay, so what I was saying that we have.
Ma'am, how do we detect these? Like in what wavelength?
These are opticals.
Okay.
You can ask statement question. So, what I was saying that for this structure we have during similar time we developed a theoretical understanding of it, and because of it we had certain equations for this structure, and we try to simulate or model the structure using numerical techniques or simulations, something like that, and this is outcome from such a modeling. So, to me, both these are statistically similar. Do you agree with me if I say the two structures are statistically similar? So, what I mean by that? So, both structures, you can see a pattern, similar patterns. For example, this thing called voids. There is in a large area there is no galaxy or distribution of matter. Then in this structure we see a thread-like structure. Sorry for that. Yeah, so we have some thread-like structures. So in both things we can see the similar. There are large empty regions called voids. There are dense matter clumps. So this is what I mean by statistical similarity. Yes.
Ma'am, how are you projecting the three-dimensional universe into a 2D plane, and how are you representing?
So this is a thin slice. Let's say for first observation. So this is observation in our northern plane. Okay, northern celestial sphere, and around the two directions, and it also spans some vertical distance in some declination. If you know the RAD coordinate, this is the RA, and some kind of elevation patch will be there. It's not just a thin slice, it's a thick slice, right, of certain width. On same for the simulated results also. For that I can say that this is a 10 megaparsec thick slice. So whatever comes with that in that 10 megaparsec slice, all of that is plotted. So this is just a word which I have said that is a statistical similar. But to quantify it, we actually need some measures, statistical measures. So what are different statistical measures? So for example, all of you must know about Gaussian distribution. So Gaussian distribution, when you see it, it's some random distribution of data. So like whatever the noise you see in your old televisions, that's some noisy distribution. But we know it is characterized by two things: its mean, its deviation. So all it boils down to two parameters. So similarly, there are different statistical measures which we can calculate from this distribution and that distribution, and they matches equal they are inside. So that's what I mean by statistical significance. Okay. So I'm going to talk about one. I need a talk. About this also. So we are going to talk about a correlation function. So let us take some volume. So, and let us say there are only 5 objects in this volume. Okay. Now I will form a pair of objects. So whatever this number of pairs that we form. So there is some length of these different. So let us say the length will form some distribution. Some will be shorter. Let's say 3. Let's say some other will be 5. Similarly, so whatever number of pairs which we have formed, we have some number. And we can then plot a histogram of this. So this, let's say the distance, the pair distance varies between 1 to 10. So on the x-axis we have 1 to 10. And in this, let's say 1 to 2, 2 to 3, in this kind of thing, we count how many pairs are there. So let's say for 3, we have 2 pairs, then we have to plot the 2 and something like this, y. So we'll get some for these pairs. This is called correlation function. And when we, so each individual point here, so here I just talked about 5 points. There are many billions of particles. We can calculate their pairs and we can form this distribution. It's called correlation function. And when we calculate from this method, then that exactly matters. That is the statistics. There are, yes.
Ma'am, in this case, is it happening that you are taking all the planets or all the
These are just galaxies.
all the galaxies that are present in a spherical distance? Like if I take a sphere according to our center, which galaxies are present in that spherical distance, that are taken into the measurements.
No, I'm not able to understand.
Like if our Milky Way galaxy is taken to the center, at a distance, if we take and take a sphere of that,
Right.
so every galaxies that comes into the upper part of the sphere, that is counted and plotted here.
So here, these are not like, so what you are talking about, so for us observing, if we do not have the distance data, everything is on the same celestial sphere, right? We don't have information about distance. So in here, for this plot, we have information about distance, and good that you point out, because then, so I also wanted to talk about the concept of redshift. So let's say 1 billion years ago, there is some galaxy, and a photon is emitted at that time. And as we know, the universe expands. So photon wavelength also expands when it comes to us, right, 1 million years later, right? So the emitted photon there might be the blue light, but as it travels through the universe, coming towards us right now, it might be some redshift. So we have redshift data for each of this object. That's why this is, we can plot it according to the distance. So this is actually the distance.
Excellent. Can you please explain correlation function once again?
Okay. So it's just a pair. So let's say this is some field, and in each box you have some number item. So what you can form a distribution of it. Let's say the value of this varies from, let's say, 0 to 10, right? So if it is a random distribution, let's say it is based on Gaussian distribution, whose mean is, let's say, 5 and variance is 1. So that Gaussian distribution will be peak around, let's say, 5. The sigma will be 1 and you will form some this kind of distribution. Meaning what? So there are maximum probability in the box and number which you found. The maximum value will you get, that is 5. Repeat 8 times. Not. So think, as you go away from the 5, the probability of finding that value in the box is less and less. Here I talked about the random number in the box. Right? Instead of this, now I am talking about not the individual box, the diagonal distribution, and I am not talking about the value here. I am talking about this separations. So this is called 2-point correlation function. Why? Because I am seeing distance between 2 points. There is something called higher statistics. So in which we see, let's say this is 2-point correlation function where we see the distribution of pairs or correlation function, 2-point correlation function. If we see, let's say if we are looking at the triangles, there will be there are 3 side lengths of triangle, and here it is just one single number among 2 distant particles. There is some configuration in the triangle. There will be different shapes of triangle, different side lengths. So for each of these triangle formations, you can count those. This is called 3-point correlation. In a higher step, nobody stops us from going on higher. So you can look for the squares and all for the paper ones exams. But we do not need that much. We will just talk about the pairs. It's called correlation. For this project, so it is a local density. So the color,
like the yellowish one, the reddish one, the greenish one.
yes. So the more reddish it is, the local density around it is higher. The more the point is in white, you will see more green color. The more the points in the dense region, you will see the red color.
So red will be the denser one, then
Red is the denser.
Ma'am, as the universe is expanding and the distance between 2 galaxies are also changing,
Yes.
then this distribution data is meant to be changed and
Yes.
with time, right?
Yes. So here, so what we do is we scale down. So let's say 1 billion ago, years ago, there is certain size of the universe. Now it has, somewhat bigger than that, right? But this physical distance between 2 particles has changed. But we scale it down to certain reference sphere, let's say. So the coordinate separation is the same, and the physical separation is different. That depends upon the expansion of the universe. What I am talking here is the coordinate separation, which will stay the same as even the universe expands.
Ratio is same.
What say?
Ratio is same.
Ratio meaning
Ratio.
ratio of
Ratio of the distances of different galaxies.
Yeah, you can say like that also. It's just scaling, rescaling as the universe expands. Let's say I have a 10-meter sphere, and later on it becomes 20 meters. But the 2 points here, they are not separate, moving as well. So it will just scale down it to 10 meters.
as I see that like the redshift is increasing,
Yes.
the red become more in population.
This one? So
Yes.
as this redshift is increasing?
Redshift is increasing, red will become more in population.
Yes, exactly.
Does it mean that early universe has the denser things and the
No.
more population?
It means the denser region are generally high in mass. So as we look, more and more in mass, the fainter galaxies we cannot, detect them. So this is of our telescope bias. You only see the high dense region of the past. In the nearby universe, we see all faint and all of them. So yeah, good point. So yeah, as I said, there are many such statistics. I just explained correlation function because it is needed further. Apart from that, there are others, many statistical measures one can look. So in my thesis, I have looked at this one correlation function. There is something called galaxy number count. So galaxy number count as a function of mass and time. So that I have looked at. Then I have looked at the pair velocity distribution. These are we'll look into it if we get time. So for now, let us just establish some basic for this kind of works. So we'll not go any further detail to the GR, but I will try to give you what it is. So it is assumed that universe is spatially homogeneous and isotropic. So when you say homogeneity, on what scale it is homogeneous, that you have to figure. So you saw the distribution of galaxies. So if I let's say these circle and this circle is around let's say same radius, but it is not homogeneous on this scale. Here you saw the large one, then you see the large density. But if I draw the sphere like this, it will be more homogeneous compared to the smaller circle like this. So when you talk about homogeneity, you have to ask on what scale it is homogeneous. So it is brilliant that the universe is homogeneous on and isotropic, meaning there is no spatial direction. In any direction you look, you are statistically you are going to get the same distribution around. And this is supported by observation. And a distance, the space-time distance in such a universe is given by Friedmann-Robertson-Walker matrix. Friedmann-Robertson-Walker matrix. This is which is written over there. Now, to just give you idea where it is coming from. So, in your coordinates, it's r theta phi. This is your normal spatial distance, r square, and the angle. And if you ignore this, this is just your r square. So this we include because there are multiple possibilities that universe might be flat, might be open, might be closed. So to account for that, we add something like this here. For this top, you ignore this, we'll keep this 0. So it's just r square and r square d omega square. Right. Now, this is the static space. As we say, universe is expanding. So to account for that, let's add some factor called scale factor, A of t.
Is this homogeneous and isotropic observationally verified?
People have conducted the calculations, and for different data sets, if you look into the homogeneity of galaxy distribution, that will come something different numbers. If you look into quasar sample, let's say supernova sample, it will be different, but broadly on a large scale they will converge. So yeah, this is kind of observation verified. And one observation also comes from CM. This is fantastically we can see this homogeneous only. Okay, so this is space part. Universe is expanding to account for the time. As you said that the 2 points are static, but since universe is expanding, they are moving away from it. To account for this, let's add some parameter A scale factor called A of t. It depends on time, and then actually time separation. And this so for physics should not depend on the reference frame, that you must be knowing. So what I am coming to, why there is negative sign on dt? Because this distance is scaling, is reference frame invariant. So that's why the time and space have opposite. You can also, alternatively, you can also put the negative sign here, and that one is positive. Anyone is fine. So this is your
What was the full form of that?
full form of Friedmann Robertson Walker. So I just forgot to ask. So what is the audience group? I mean, how many of you are first 2 years bachelor's? Okay. And how many of you are in physics major or something? Okay. And PhD first. Okay. Good. So now we want to see how the universe expands. The only time quantity, the quantity that depends on time is scale factor. All other things does not depend on time. So to see how universe evolves in a time, it is useful to derive this quantity. The first derivative of the scale factor and the second derivative of the scale factor. So these are basically the speed with which universe is expanding, the first equation, and second one is acceleration with which it is expanding. And when we calculate using GR, we get this. This is right hand side, right? We get this on the right hand side. So you see there is a energy density rho here. This curvature constant kappa, same thing. This pressure P. There is something called lambda, cosmological constant. We have to include it to be, consistent with the observation, but nobody knows physically what it is. But yeah, these are so mainly, as I said, we'll only look into the flat universe. So this is 0. So broadly, the scale factor evolution depends on energy density rho and pressure P. Pressure and energy density of what? So there are different constituents of the universe. There are photons, there are matter particles, there are some fuzzy dark energy dark matter particles. So it's a pressure and energy density of those things. So you can recall that in your kinetic theory of gases there is a relation between pressure and density. So if you remember this factor of 1/3, So there's such an equation called the relation between pressure on energy. There is some factor. It's called equation of state, like this one. So for the kinetic theory of gases, you must be having 1/3 here. P is proportional to 1/3 of your energy. Right. So for different constituents, this is what I have talked about is the atomic gas. But for photons it is 1/3. If you have different degrees of freedom, this omega will change. For matter it is different. So if you take corresponding equation of state for W, for example, photon is 1/3. Put the 1/3 in this. So when you combine this equation, so take the derivative of this, put into this, you will get this equation. When you do and when you solve for it, you will get energy density evolves with the scale factor like this. What it means? So if you put the omega for photons 1/3, you will get the energy density of the photons decreases in the power 4 as scale factor. So as the universe expands, your photon energy density decreases in the power 4. Similarly, the matter energy density decreases in the power 4. Or dark, this is lambda, same the constant. We call it as dark energy. Since it is a constant, it stays the same, and as this is not there for our case, but for you it decrease in power curvature energy. Okay, so it is now these are the energy densities in the universe. How do you know what are they? What are their values? So we again from the observation know their values. Their values are presently known. And it is found that the late time evolution of scale factor is majorly governed by two things. One is matter and another is dark energy. Now since they both vary at different rates, this is a scale factor on x-axis and this blue curve, those are for one is called matter, one is called dark energy. And since they both vary at a different rate, they are going to have same. They are going to match at some time. And this is what it is basically telling is, so percentage contribution to the total energy. There are different constituents, there are photons, there are matters. So if you at given time, if you calculate what percentage of energy is coming from radiation, photons, what percentage of energy is coming from matter, same thing. So for this epoch, this scale factor, this is called the contribution to total energy is 50-50. 50% is coming from matter, 50% of coming from dark energy. So this is some very recent scale factor. This is current scale factor. This is us at today at present, and this is our past. So at very recently, we entered into dark energy dominated era, meaning the total contribution to the total energy is majorly coming from the dark energy. Sometime before it was matter dominated. Similarly, if you go very, in the early universe, the major contribution was from photons. So it is called, so at that time, it is called radiation dominated era, when photons were majorly contributing to the total energy. And this green curve is representing the total size of total observable universe. So as time increases, the size and volume of the universe which we can observe, this is because the speed of light is limited. So this grows like this. And in the dark energy dominated era, this is the speed with which it was increasing. In the dark energy dominated era, this gets slowed down. And in the future, it is going to stay the same. Meaning what? In the future, we are going to be kind of alone. The maximum universe which we can observe, it is already in the past, the maximum size. Now we are at the same value. It is not increasing.
Does this graph show that the dark matter was originally zero but it started from scratch?
Originally zero, why was it zero?
Because the dotted blue line is representing rho lambda. That one is going.
This one is rho lambda. And you are saying this is rho lambda, this is matter.
Yes, so dark matter is originally zero.
This is one value, 10 raised to 0 is 1.
No, that is for matter. For
Dark energy, you are saying it was 0.
Yeah.
Okay. It's not 0, you cannot say it is 0 because 10 raised to minus 2, 0.001. And these are exponential scales. So what happens on this, on very early Big Bang or at least I am not expert of those kind of physics, so I don't know. But yeah, for those waves shown here, those are the values, and we can say it is 0 up to 2 decimal points, but at least it has value after 2 decimals. So this you must have seen frequently. This is typical timeline of the universe. So as I said, initially very early time, the universe undergo very rapid expansion within 10 raised to minus 30 types of second, just to do very I don't know how many fold, but really huge amount of size it has in that tiny fraction of second. After that, the universe passed through different phases, like this earlier the warp plasma, then there is formation of elements, then there is as I said, the early times, the total energy contribution by photons was the highest. So radiation, that is called radiation dominated era. Somewhere here, radiation dominated era. Then matter started dominating the total energy. We start somewhere here, the matter domination era. And here, what happens is this photons and matter is coupled, because of which there is no formation of stable atom. As soon as atom used to get photon try to break it apart. So there is no formation of atoms were forming but not stabilizing. This sudden, as the universe expands, it's getting cooler and cooler. The photon energy drops. So the photon now try to break the atom, but it is not breaking. So suddenly, this is called epoch of reionization. This is suddenly photons were unable to break the atoms and stable atom got formed, and this is called epoch of reionization. And then obviously the light which we see is from the galvanic matter. So that got spread across the all the space, because of which there is no concentrated sources of light. That's why this very large amount of time is called dark ages. Universe was dark. There is no source of light for many longer time. So this is called dark ages. And after very sufficient time, the gravity played a role. It tried to bring this matter together, and then very later forming first generation stars, then galaxies, and all. Then that the light which we can see today is called formation of first stars or sources of light, somewhere here. Then later on, the dark energy dominated era, and we are here at present. So the thing which I have just explained in the words was, before that there is one point that, yes.
Ma'am, if the universe has started from a single point, then after that explosion, the light that was created that time already started to travel very fast with the speed of light.
Okay.
Right? Then the matter started to expand. The universe started to expand. So the matter speed must be less than light speed.
Okay.
So if the matter speed is less than light speed, then how can we observe the light that is coming from the beginning of the...
We are not observing. There are two parts. The light which, the galaxies which we observe, that sources of light is formed very recently. So, as I said, this formation of first sources of light somewhere here. The galaxy from light which we see is there. There is another source of light which is CMB, you must have heard. CMB is coming from here. We cannot see beyond this. So light, the light which we are seeing using our telescope is only of two kinds. First is here, the formation of first source. Second is CMB photon that got free streaming when stable atom got formed. No. So beyond this, we are not seeing any light coming from earlier universe than this. So that's our belief.
So ma'am, we can also say that after forming that blue area, yellow area, it sustained for a longer time, so that
what sustained for the longer time?
The elements that created in that area or that era.
This area.
Okay. So it sustained for a longer time, so that the matter particles and universe can expand much more. And where we are now, the light that last emitted from there from the billions of years ago, it at least sustained till that date.
Till this point? Yes, the CMB photons.
I'm saying that not only the light but also the matter particles that was present, that was present till that date when we are measuring the light.
Not getting your point.
Like universe started to expand,
right.
Yellow region formed,
right.
and some part of the yellow region sustained, other part started to expand the universe.
Why you are saying some part is sustained?
Because when it is sustaining, it is constantly emitting the lights, and after we are getting here, then when this light started to emit it for the last time and we are reaching it right now. So it must have sustained that for some time at least. You can say for a longer time.
What do you mean by sustain?
Like
Big Bang explosion में light नहीं था. It was not a bomb.
मैं कह रहा हूँ वो जो yellow region है वो
dark
sustains whatever the source of light in
नहीं,
that area.
source of light was not there. Source of light will come after star formation.
We'll clear that out. We'll be problem. Okay, so it will clear it. So plot, I will show the plot. So yeah. So for now, the point I am making is we are yes.
Also, do we know why did that happen at that particular time? Like why
Recombination might happen at that particular time.
why is the dark area only that long?
You are talking about this region, right?
Yeah.
Okay. So what was the first element that is formed? Obviously, hydrogen. One proton and one electron. Right. So at that time, So you must be knowing that to ionize the hydrogen atom, you will require 13.4 something electron, something like that. So the early photon were the photon energy were larger than that. This is the time when photon is so much cooled down that it is below 13.4. It cannot ionize the hydrogen atom anymore. That's why the atom, the photons, the cooled photons could not take the atom. That's why that particular time it is happening. Yeah. So so my thesis is mostly was on structure formation, which mostly all of the time deal with the matter component only. Okay. So this is basically equation for solving this particular. This will complete later. What I was trying to say that in very early time, the problem of structure formation is in the linear region, meaning where you can actually take a pen and paper and solve the equation in this yellow region. It is called linear region of structure formation. You can obtain a solution for structure formation equations in yellow region. But as the structures get more and more concentrated, these galaxies get formed, it is very hard to solve the structure formation equation, and that happens in this blue zone. And it is not possible for generic universe. It is not possible to solve this kind of equation in that blue zone. So what majorly people do is the blue zone is studied using numerical techniques and specifically called simulations. So that is the tool which is majorly used in my thesis. We'll get into that, but before I am coming to this plot, you asked something, right?
We are still in flat space, right?
Yeah, we are still in that. Okay. So whatever we see said for this the picture. So same thing is pictorial, the graphically represented. This is a scale factor. So this is how universe is evolving. This is current time. This is earlier time, and there are two kinds of matter. Okay. One is barionic matter and one is dark matter. The galaxies, the light which we see in the sky, that is called barionic matter. The dark matter is also there and we cannot see it, but we know somehow it is there. So, out of total matter, only 15% of matter, that is the barionic matter, the matter which we can detect. And 85% of other matter which we cannot detect at all. It is called dark matter. Right. So, in this plot, so let us this universe, there is distribution of matter. Let us go to some point where there is a slight higher density than average density of the universe. It is called delta. So it is the deviation. So you have the universe, its average energy, let's say some value. You go to the specific location, and there the value within, let's say some region at that specific location, the value is slightly higher than this average value. So we'll go to that point. It's called perturbation. And as the universe evolves, since gravity is attractive, so there is some over density. It will try to collapse, matter get accumulated, and this the perturbation delta. So as the universe evolves, this perturbation is going to the matter is going to come together. Meaning what? The deviation from average is also going to increase. The average is going to stay the same all the time. This is going to increase with the time. So this is called delta perturbation on the y-axis. And this is how the two perturbation. This is for dark matter. The solid one is for dark matter, and this one is for barionic matter, which we actually see. So dark matter perturbation grows like this. As it is, dark matter is okay. Yes.
Gravity is the main force for introduction of the perturbation.
Gravity is the
main force for introduction
No. The origin of perturbation lies very early in the universe. These are quantum fluctuations. So as I said, at Big Bang, inflationary phase, universe goes sudden expansion, and the size of the universe was so tiny, the fluctuations there were quantum. Since it suddenly expanded, all those fluctuations get imprinted on the matter distribution at that time. So these are quantum level fluctuations, suddenly grows and becomes non-quantum size. These are the, so as we say, universe is homogeneous, but it's homogeneous on large, but locally there are perturbations. Somewhere you are going to see the value below the average density in the universe, somewhere you are going to see above the, so that is the tiny fluctuations are there. At very initial time, these tiny fluctuations, so even these are very tiny fluctuations. Let's say 10 to the power minus 5 order of fluctuation. Let's say if the average density of the universe is 1, then these kind of perturbations are 1.00001. So these are that much tiny, but this much tiny fluctuation is enough to see the galaxies that form today. These are really the large galaxies which we see. These are really the quantum fluctuations at very early times.
So these, like in the very early universe, you said about quantum fluctuations.
Right.
These happen in like some sort of like a scalar field or some field there, or like?
Yeah, I'm not an expert of but people. So this field is there are no much observational evidences for it, but people try different models. There are the scalar field theories, there are other medicines field, there are many theories, and those are, as of now, these are theories only because there is no observational evidence. But yeah, there are theories.
So, like you said, those fluctuations are imprinted on the matter. So, we are assuming that there is some matter coupling to this field.
Yes. At very early years. I am not expert of it. So that's how I think. Yes.
How did you got that dark matter perturbation?
What do you mean by?
The board trees there.
So you are saying what that plot is representing?
How do we get there?
These are Boltzmann code. Have you heard of it?
But
Yeah, say it.
no, I was thinking if we can't detect it, then
Okay. So these are theoretical curves. We cannot detect it right, but we cannot detect it directly. We have lots of indirect evidences that there is a dark matter, and those are very strong that we cannot ignore. Those looks like a very robust theories of dark matter. So the curve which you are saying is a theoretical calculation, but based on what we indirectly see about the dark matter.
what kind of evidences?
Okay, good. So there are many. I will just say one or two. So you know the Kepler's law, right? The square of the period is proportional to the period. There is an assumption in this derivation that your mass is concentrated at center. Where do we apply this Kepler's law? To the solar system. Because Sun forms 99% of the matter and remaining 1% is all the planets, right? So mass is very much concentrated at the center. So you can apply the Kepler's law. Now, let's take some example galaxy, right? At the center there is very high concentrated matter because we see these aliens, and as we go far from the galaxy there are these arms, other planets. So what we see in the galaxy, we see the same thing, that 99% of the matter in the galaxy is concentrated at the center. So it should also follow the Kepler's law. But when observers actually measured it, it wasn't following the Kepler's law. So one solution to this was the first assumption that the matter in the galaxies is concentrated at the center. It is not correct. There is some, the matter which we are not seeing, and that is changing this Kepler's law, square of the period is proportional. That is one evidence. Another evidence is gravitational lensing. So we know from this GR prediction, sun is there is some beyond the sun there is some star, and because of the sun's mass, we see the deviation in photon path, right? So the star is here, but we see it here because photon path is get diverted. Similarly, when we actually observe these galaxies in the telescopes, these are not point objects. We see some distortions, and there is nothing between. Let's say there is some source here. There is nothing we can see in between, but still it deviates some in different manner than what we expect. This meaning what? There is some thing in between which we cannot interpret as according to our electromagnetic our knowledge. So this is another. This I can suggest you some references later on if you are really interested to in the evidences for document. But dark matter is very robust finding. Yeah. So dark matter how it evolves, and the matter which we see how it evolves. So there is visible difference how it evolves. So what happens with the dark matter is there are phases in the universe. Earlier there was radiation dominated, then there is matter domination and so on. As we saw, there's in the radiation dominated era, there is a speed with which universe becomes different. Same affects here. So in the radiation dominated era, it was varying with the different speed, then speed changed, and then in the epoch of in the matter, this slight change of flow here you cannot notice, but there is change, and this perturbation flows, meaning matter is coming together up to the point of point. So why this is perturbation amplitude 1 is important, that I will come to later on. In the baryon cases, so baryon is baryonic matter is electromagnetically interacting with the photons. So as I said, where these fluctuations get imprinted on the matter distribution, simultaneously it was imprinted on the photons. So where there is large number of photons were there is also large number of matter. So matter is reacting to the gravity, coming closer. As matter starting coming closer, there is photons also. Those are also with that perturbation coming together. But photon has some pressure, they are interacting with these atoms and all. So they try to push away this matter. But again, after a certain time, that magnitude got dilated again, starting to come in together. But photon pressure will increase, they start to take it out. So these are basically oscillations in the density here, right?
Now why does it get diluted?
What doesn't get
You
diluted?
said no, the pressure pushes apart, but the magnitude is diluted. When you said something is diluted, that's why
so in case of dark matter or in case there were no photons, what would happen? There is no dilution. What I mean by dilution, so at this physical location, there is a overdensity coming closer, right? If there is no photons, it will continue to come closer. Since there are photons and there is pressure, that photons are trying to spread this overdensity to the bigger, so meaning dilution of this overdensity. That's what I'm saying. Okay, so this goes on. Matter trying to come together, photons trying to separate. So these oscillations. So these oscillations which you see, and this was the important epoch as we discussed, that at epoch of reionization what happened? Stable atom gets formed, and suddenly this something called scattering cross section. So why earlier there was this interaction large amount? Because there was electron, proton plus photons too. Suddenly the electron proton got merged, and there is plenty of space is available to these photons. So these photons just got, they are no longer limited to this physical space. They just free stream over the entire universe. Now this overdensity in the matter that remained there, right? But it was coupled with the photon, so whatever the overdensity was there, it just stayed there for the same. with the meaning there's no physical feature in the matter also at that time. So what happened at this point? There's no coupling. The coupling between photon and matter ended. So baryons don't know what to do. They just stayed there. But there is a dark matter present there, and baryonic matter also react to. Baryonic matter react to electromagnetic forces as well as to the gravity. So gravity was, the dark matter thing was there, so it just started following the dark matter, and again it catches this dark matter here and grows. This perturbation amplitude grows. So this is a linear thing. You can see where there is a over density, the perturbation amplitude grows, meaning the over density grows, and it's continue to grow. But this is what I am saying. This is yellow region calculations, right? And those are limited to yellow region only. Later on, there is equations get changed, and so basically this is, let's not go into the details, but this is the equation. So this is this how it gets changed and how do we know it. So this is some. So there was a blue zone also. So this is what happens in the blue zone. As soon as your perturbation over density goes beyond 1, these equations, these are highly nonlinear equations. They are solid, and suddenly, so this is over density. The matter is starting to coming closer. As soon as perturbation amplitude reaches the 1, there is an acceleration of this collapse. The matter is coming together with a larger speed. So this is this thing. And this is called non-linear collapse. Right. Now these are the dark matter. So I am talking about solid right now. These are dark matter particles. They are supposed to be collisionless. We don't know what it is. We assume they are collisionless, some fundamental particle, but still we don't know. But this assumption is there. They are collision. They are ideally what should happen? They should collapse to infinity, right? Mathematically, it should collapse to infinity. It should come to the. But this is not how physics works. So what happens? These are collisionless. So this is perturbation. Suddenly it's collapsing. It passes through each, like the particles passes through each other, right? But still there is a gravitational potential here. So they oscillate like this. The perturbation collapses and this oscillates like this. So this happens with the this thing. This is about dark matter. What happens in the case of baryonic matters? So they are sitting inside this dark matter perturbation because they follow the dark matter. They are also there in the perturbation. Now, as soon as this nonlinear collapse happens, baryons are not collisionless. They have pressure. They cannot pass through each other. So there is they just go head-on collision, right? So they since because there is a head-on collision, there was a shock. Shock meaning what? There is a generation of large number of excitations of the light. So it undergoes shock, and then what happens after the shock? It's cooled down, meaning what we call de-excitation of the atoms. So it then okay. So this 1 hour is almost over. But we haven't yet started. This is the 4th slide. I have made. So what should I do?
You can continue.
But, let me. I'll just finish the introduction part. But
Okay.
still, it is a lot of it is remaining. Just I'll try to finish it.
We can make 2 parts of the talk, maybe.
Okay. That's also fine, but I don't know how it will work.
You just try to cover whatever you can.
Yeah. I'm also fine with giving, so let me know, but let me just get some completeness for this talk.
Yes.
Yeah. So let's not go into the details of it. This is how basically what we are showing. This is the master equation, which shows how these things, the thing which I have plotted. So basically these are the equations for the saints. But in this slide shows how these are derived. So if anyone is interested, let us discuss it later personally. But for for it now I will skip it. Right. So that was one. So that was about equations. So as I said, in the nonlinear blue zone, these equations are not solvable. You have to keep volume into. So it's basically Newton's law, not for the two particles but n particles. So there will be n square interactions, right? So we have to solve this n square interactions simultaneously. This is very complicated, computationally very challenging task, but that's what we do in the simulations. So this is just a representative volume. I have not yet distributed the particles according to the universe. So for that we need so it is assumed that very early times universe were homogeneous, right? So and it is given by most of the time it is given by Gaussian random distribution. Okay, and Gaussian random distribution needs two parameters, mean and variance, standard deviation, right? So mean is coming from the average density of the universe. So whatever at very early time, we'll take some very early time. What was the mean density of the universe at that time? That will form our mean of the Gaussian, and the variance, the standard deviation will come from this plot. This is called power spectrum. So for those who understand advanced everything, I'm just mentioning, we were talking about correlation function. So those who can understand, power spectrum is Fourier transform of this curve, right? Here we have pair separation, meaning distance versus the count of these distance pairs. And in the Fourier space, we will have 1 over distance and 1 over count. This is for advanced. Let's just I will just explain. So what is it? So just refer to the top x-axis. It is the same distance which I am talking about, the correlation function. So distance, and this is some kind of clustering power on that scale. Meaning what? Let's say this is 10 raised to 0, right? This is 1 megaparsec. Something here. Huh? Then this 10 raised to 10 megaparsec. So for this particular power spectrum, the clustering, the strength of clustering at 10 megaparsec is more than 1 megaparsec. That's what power spectrum says. So we need this information to distribute the particles. So we take these two information and distribute the particles, right? So these are actually particles at very early time. So look at the scale factor. The scale factor present is 1, and we have chosen very early scale factor 0.006, something like that, and we have taken this 300 megaparsec box of the universe. But this is a very finite box in the universe. The real universe is infinite. But we have selected only 300 megaparsec of it, which is not correct, right? So what we do is, we repeat these boxes in all 3 dimensions. This 300 megaparsec box, we repeat the same box here, infinitely. So we have created the infinite universe using these small boxes, but we have to worry about only this much evolution. We don't have to worry about what is happening. Why? Because these boxes are exactly similar. So let's say, for example, there is some particle here, okay, and it is evolving at later point of time. It is coming here. Now it will come out of the box, right? But there is some proxy for it in this box also. So as soon as this box exists here, this its similar twin will enter from this way. The particle number in the box is conserved, and we get the infinite universe. So this is called periodic boundary conditions. This is some advanced topic in n-body simulations. You can Google it later on if you are interested. So yeah, we have distributed the particles. Now, what we have to do? We have to calculate 1 over Newton's law, 1 over r square force, right? These are billion particles, 10 raised to 10 particles. So these are 10 raised to 10. So those will, and n square, will imagine, even if one calculation take 1 nanosecond in our computers, then we should take into cos square, then we should 20 interactions. We need to calculate at 1 time scale, right? multiply or one calculation with 1 nanosecond, let's say. So still it is how much? 10 to 11 seconds it will require. So convert the 10 to 11 seconds into your days or number of years. You will find that this will take 115 years. But we also have parallel programming. So these are some advanced computational things. So these are actually my simulations. With the parallel programming, we reduce this 115 years to 3 months. Okay. Yeah. So we calculate the forces and move the particles. This is just for one interaction. So we move the particles, evolve the simulation, go to the next step. You say some kind of lumpiness is there, where there was some kind of this is under density, this is over density, this some kind of fluctuation in the field. And earlier there were some under density became more under density, where there is over density become more under. So it's basically accident. So notice where there are brighter and darker regions. I will show you the next time slides. You notice whether that is enhanced or reduced. Let's go to the another time step. So where there is under density, it becomes further under density. Where there is over density, it becomes further. So it's going on. Let's go to the further time step. Now it is visible. Like it's forming thread-like structure, and under densities are really under density, and there is some foam-like structure is getting formed. And this is at the current time. So this is entire thing the simulation is running on, right? So this is at the present. So we have some very high dense regions here. These black things are this under density. There's no matter at all. I should not say at all, but it's very little amount of matter in this darker patches. These are your so this is our distribution of dark matter at present, and we find it out using simulation. But we don't see this now when we take a telescope and or with our eyes. When you look up in the sky, we don't get to see this, right? What we see is something like this, right? At least the first image which I showed for the SDS, the observation, it was very similar to this, right? So what is this? This is the biased light that is coming from the barrel. So as I said earlier, the light which we see, there are 15% of matter, only that kind of matter emits the light. And where that matter is present? Not randomly, but that is present along with the dark matter. Where there is a dark matter, there is a matter. But is the reverse true? Can there be a high density in the dark matter, but no high density in the barrier? Right? So let's say you must have seen those, on Diwali, the NASA publishes a photograph of India, right? Where there are cities, you see the very high light, and in the very, let's say, very jungle or hilly area, there is no light. So you see that map. Now let's say I want to deduce a population information from that map. Right. So what I can say, where there is light, there are people living there. Sure. But where there is no light, can I confidently say there are no people there? This is bias, right? So same thing. Where there is this light, there is a overdensity. But where there is a no light, we cannot confirmly say this is overdensity or no. Same thing. So this is that's it. I should stop. This is about introduction. There are many more topics. Let me know if we can arrange it. Yeah, that's it. Thank you.